Okay, let's find the derivative here of this algebraic expression that's implicitly defined as a function of x, and we're going to use the implicit differentiation. So we're going to evaluate -3, -1, but we're also just going to find dy dx explicitly in the end, just to work on the algebra a little bit. So what we said, we want to first take the derivative on both sides, d dx of all this stuff, x plus y quantity squared plus y, and then equals, and then d dx of 15. Okay, so over here we have a chain rule. All right, we have x plus y inside, 2 outside, the power function 2, the second power function. So we're going to have 2, keep everything inside the same, and then multiply by the derivative of the stuff inside. Make sure we put in parentheses the derivative of x with respect to x, 1, the derivative of y with respect to x. We're just going to use dy dx here. And then we have plus the derivative of y, which is dy dx, and then equals here 0. Okay, so this is a case where solving for dy dx here sometimes becomes problematic in terms of the algebra, right? So sometimes what you want to think of, what would I do if this was x plus 3 and this was, 1 plus x? What would you do? And hopefully you think that if this was x plus 3 and 1 plus x, you would multiply everything out. And that's what we're going to do here. So we're going to distribute 2x to the y, and then so 2x times 1, 2x, 2x times dy dx, so plus 2x dy dx. Then we have 2y times 1, so plus 2y. Then 2y times dy dx, so plus 2y dy dx. And then plus, we have the dy dx here, equals 0. Now we want to get all our dy dx's together, so we're going to move the 2x and 2y over. So that gives me 2x dy dx plus 2y dy dx plus dy dx. So I'm going to factor out the dy dx. So that leaves me with 2x here, leaves me with plus 2y here, leaves me with plus 1 here on the left. On the right, I move the negative 2x, move that over, minus 2y, right? And then we have this end result here. This end result, when we divide both sides, we get dy dx equals negative 2x minus 2y divided by 2x plus 2y plus 1. Okay, so there's dy dx. In the end, try to zoom out a little bit here. Let's see. Okay, so as we look at the end, right, we want to evaluate at -3, -1. So we can plug in the -3 for x, -1 for y here and here. Okay, like I said, if you're going to find dy dx, and we need to find dy dx, we're just going to do this. Okay, if the question is not really to find dy dx explicitly, what the derivative is in terms of x and y, then we're not going to do this process. We'll go right up to here, right, from this point, right in here. And now we're going to sub in -3 and -1 right away. So this becomes 2 times -3 plus -1, -4, times 1 plus dy dx, plus dy dx equals 0. And now this is going to become more familiar to solve. We have -8 distribute. So -8 times 1 minus 8 dy dx's plus 1 dy dx. Okay. Then we're going to have what? Bring the 8 over. Here we have -7 dy dx's equals 8 divided by -7. And we get the value of the derivative at -3, -1, which would be -8/7. Okay, so If we're going to evaluate the derivative, might as well plug in before we solve for dy dx. Okay, it's just going to make the algebra a little easier. Okay, if the goal in our problem is just to find dy dx, then we're going to have to solve it and do the algebra with the x's and the y's and the dy dx's. Okay, so there's another example of implicit differentiation. And now let's go over here. And on this one, we're going to find the second derivative of y with respect to x. Okay, so this stands for the second derivative. And generally, we want in terms of x and y. So in the end, we want this in terms of x and y. So to find the second derivative, we've got to find the first derivative, right? So we take the derivative on the left, the derivative on the right. So to find a higher order derivative, you got to take a derivative and then another derivative. Here we have the derivative of x squared. The variables are the same, so 2x. Take the derivative of y squared. The variables are different, so we're going to have 2y. And then times dy dx, or y prime if we're using prime notation, equals 0. Okay, so take your derivative, solve for dy dx. Right, we've got to find our first derivative, so dy dx. Right, is going to be, move the 2x over, negative 2x, divide by 2y, so we wind up with negative x over y. So here's our first derivative. Right, now to find the second derivative, we just have to take the derivative of this. So take the derivative on the left, take the derivative on the right. Well, the derivative of the derivative is just the second derivative, so that just gives me the second derivative notation. Now over here, we got a quotient rule. So we take the derivative of negative x with respect to x, which is negative 1, times y, minus negative x, so minus negative x becomes plus x, times the derivative of y with respect to x, which is going to be times dy dx, all over y squared. Okay, and here we can see that our second derivative is in terms of x, y, but also dy dx, the first derivative. All right, and in the end, we want our second derivative in terms of x and y. So then all we have to do is replace dy dx with what it is, negative x over y. So we plug it in here, and we then would have our second derivative would be negative y plus x times, there's dy dx, negative x over y, and then all that is over y squared. Okay, so there's our second derivative in terms of x and y. So that's all there is to higher order derivatives when we're doing this stuff implicitly. Take the derivative, take your derivative, right, implicitly, solve for dy dx, then take the derivative again, right, and then in the end, you're going to have a dy dx or a y prime, go back over here, wherever that first derivative is, and just replace it. Okay, that's all there is to that. All right, so check this over, watch it, take notes, all right, rewind. If there's any point here you weren't sure of something, just make note of the time, and then let me know. We could go over some more detail, okay?